Hi, everybody. My name is Megan Peters, and I'm going to be presenting work done by Jarrett here for his senior undergraduate thesis entitled Variance Misperception Under Skewed Empirical Noise Statistics Explains Overconfidence in the Visual Periphery. So in everyday life, our visual system must make decisions based on noisy information. So if this is you and you have a brain and you have eyeballs and you are driving down this foggy road, you think you see something up ahead here, and you have to decide what that thing is. Is it a deer, a car, or a tree? So your system decides that this is a car, and you also feel a sense of confidence in this choice. This confidence judgment is what we'll focus on today, and it requires that the metacognitive system form an estimate of the noise in its own representations and its decisional process. But how does the brain estimate its own noise? One kind of obvious default answer would be that it doesn't estimate noise, it just knows noise. If the brain is an ideal observer, then it has perfect access to the noise in its system, and it can use that to make metacognitive judgments. This here is a graphical depiction of a two-dimensional Bayesian decision system that might operate under this ideal observer kind of rule. We have some evidence that metacognition might be optimal like this. So in this paper from a few years ago, we used forward-backward masking to render visual targets difficult to see in two sequential intervals. And we set a floor on confidence by making one of the targets physically invisible or absent. We asked participants to discriminate the identity of the target in each interval, and then we asked them to rate their confidence on each pair of intervals by betting on which of the two decisions they felt more confident in. We built a Bayesian ideal observer computational model, and we simulated what the results should look like. So you can see as target contrast increases in the target present interval, which has that non-zero target in it, performance is going to increase. And also the model shows an increase in confidence judgments, which is an increased ability to bet on its choices in that target present interval. The human results across a number of experiments ended up matching this ideal observer remarkably well, which suggested to us that under this paradigm, which is free of response bias in the confidence judgment, humans behave as if they have optimal access to their own noise. But let's make sure that's the case, especially if we abruptly increase the amount of noise in the system, like this. We can use a single pulse TMS to add noise to primary visual cortex using a similar paradigm as before. We zap you when there's a target, and we don't zap you when there is no target. But now this ideal observer fails. The model predicts that TMS injected noise ought to decrease both performance and confidence, see here in the black line. But the humans, the red line, do the opposite. They increase their confidence even as the noise made them worse at the task. So to explain this result, we created an alternative model. Instead of having perfect access to its own noise, this new model is completely blind to its own noise. It just assumes the noise has not changed, even though the noise has massively increased due to the TMS. And this blind heuristic observer now predicts human behavior really nicely. Predicted confidence now increases with increasing noise rather than decreasing with it. So this shows that humans might actually be blind to their own noise, or at least estimate noise in some suboptimal way. So now we have competing theories that can explain the data in different experiments. Either the human metacognitive system is optimal, or it's suboptimal somehow. But if it's not optimal, how exactly is it suboptimal? And we figured, well, everything else in perception is well described by Bayesian inference. Everything is Bayesian. So why should metacognitive noise estimation not also be Bayesian? So to see if this works, we took inspiration from the observation that a weird phenomenon seems to happen in the periphery of the visual field, despite the fact that the visual system has poorer signal-to-noise ratio in the periphery than in the center. We feel like we can see quite clearly in the visual periphery. That is, our experience of our visual world is much more like the photo here on the right than the photo on the left. We experience an inflated sense of confidence in the information being processed in the visual periphery, relative to the accuracy that the peripheral retina is capable of supporting. So this gives us a really great opportunity to study how the brain estimates noise for metacognition, because performance and confidence become naturally dissociated without any external intervention from us as experimenters. And as in all Bayesian models of perception, we can also take inspiration from a great many fantastic studies which show that the perceptual system is sensitive to the statistics of its environment. For example, our brains have learned that light typically comes from above, and the computational result of relying on these learned expectations is that these little things here look like bumps, and these guys look like dimples. And we know that this is due to learning because you can actually change it with training. And likewise, we know that the system has learned that vertical and horizontal orientations are more likely for edges in a visual scene, and that the system uses this prior knowledge in a Bayesian way when making orientation judgments. So we figured, what if the visual system forms prior expectations about noise as a function of visual field location? In the center of the visual field, noise is likely to be low and relatively stable, not have a lot of variance around it. But in the visual periphery, noise is going to be overall higher. And because noise can't be negative, it's likely to have a positively skewed distribution. Sometimes the noise might actually be really high. But maybe the system doesn't know this. Maybe the system knows that peripheral noise is higher than central noise, but not that it's positively skewed. Could this one error be enough to explain peripheral inflation? So to answer this question, we built a whole bunch of different models, and some of them were even inspired by previous literature. Each of the models here uses the knowledge of noise statistics like this in a different way. So some of them have optimal, perfect access to noise, or have perfect access to noise statistics and use that knowledge in a Bayes optimal manner. Some of the models are totally blind to changes in noise, and some of them estimate noise in a Bayesian or heuristic way, but imperfectly, maybe relying on the wrong noise prior. And I'd like you to keep an eye on model 5 here. That's the one that makes this one mistake about noise statistics in the visual periphery, but it does everything else in a Bayes optimal manner. It uses prior expectations about noise that just happen to be wrong, and combines them with online noise estimates to get a posterior estimate of current noise. And so we draw a bunch of samples from these different noise distributions, and we simulate the behavior of each of these model observers in making decisions and confidence judgments under a bunch of these different noises. And here's what we found. In the center of the visual field, all of the models typically match in terms of confidence in red and performance in black. There's a slight underconfidence here for the blind model relative to performance, but every other model is really spot on. In the periphery, though, it's a different story. So only the perfect ideal observer models, this one and this one, have performance and confidence that match. The blind model and the two imperfect heuristic models predict significant overconfidence relative to performance. And this is peripheral inflation. But which of these models is the winner? All three imperfect models predict peripheral inflation. So to further arbitrate the models, we observed that some empirical results show that peripheral inflation can actually increase when you stop attending to your visual periphery. It's kind of counterintuitive, but let's see if we can get one of our models to do that better than the other ones. So in 2018, Odegaard and colleagues reported that using crowding to manipulate attention resulted in the following. In unattended conditions, we see lower performance relative to attended conditions, but there is no difference in confidence for correctly answered trials. Only if you give an incorrect answer do the unattended conditions show an increase in the confidence that's reported. So this is the pattern we're looking for. If we subtract the unattended trials from the attended trials, we should see no change in confidence for correct trials, and we should see a negative number, attended minus unattended means negative, for the incorrect trials. And we simulate all our models across a range of attended and unattended conditions. And we increase both the type 1 and the metacognitive noise when attention goes down. And we selected all of the simulated conditions then in which the predicted performance matches the empirical results. And here's the result here. Only model 5 shows this correct pattern, where correct confidence in red is not changing no matter what we do, but incorrect confidence is higher for unattended than attended conditions. So this line is consistently negative right here. And what's happening is that because model M5 thinks that peripheral noise is not positively skewed, even though it knows that noise is bigger in the visual periphery, it ends up underestimating the noise and therefore overestimates confidence, but only in this specific way that disproportionately affects the incorrect responses. We already knew from previous research that variance underestimation can lead to confidence inflation. But now we know why variance underestimation might occur. It's not just that the system is being stupid. It's that the system is using optimal Bayesian computations to estimate noise, but it's just getting the priors wrong. This is not the end of the line, of course. It now seems pretty likely that the system is estimating noise in a suboptimal way, and that incorrect noise priors might also be involved. But it could also be that there's a wrong decision policy going on or some other corrupting influences, so we have a lot more work to do. But what we do know is that these metacognitive failures can lead to confidence illusions, where confidence and accuracy dissociate. And we need to work on ways to maximize this effect, which includes measurement of these noise priors, so we can figure out how the brain is actually doing that metacognitive noise estimation. So this work is now under revised review, but if you are interested in learning more, you can see the whole preprint here on bioRxiv if you like. Thanks for your attention.